Today we're going to take a look at some log properties. We're going to look at the power law of logs, the product law, and the quotient law. And we're going to look at how these tools will help us to solve questions. So let's begin by looking at the power law of logs. The textbook has an investigation that helps us discover the power law for logarithms. It's going to ask us to evaluate the log of 2, the common log of 4, the common log of 8, 16, 32, and then look for a pattern to come up with a procedure that will help us reveal the power law of logs. We're going to do this by plugging some numbers into our calculator. So to begin, what we're going to do is first of all go to our stats. So remember that our calculator can be used as a little bit of a spreadsheet, and we do that by hitting stat and then enter. So it was stat and then enter. And in list 1, I just want to enter in 2 for the log of 2, 4, 8, 16, 60, and 32. If we want to enter a formula that will act as a fill down command, we can just type in at the very top of the column log, and then I want to take the values from list 1, so I'm going to use second function list 1. This should calculate all the values for log of 2, log of 4, log of 8, and so forth. And if we look at these right now, they look like just a normal sort of table of values. But in fact, if I look closer, and maybe even just look at the first 3 decimal places, I end up with decimal 301, decimal 602. Now those are exactly half or double each other. And so what I want to do is just paste this in so I can have a little bit better look at what that table reveals. So here's the values that I was talking about. Log of 2 is decimal 301. So log of 2 is equal to decimal 301. Log of 4 is equal to decimal 602. And I'll do one more, the log of 8, which is equal to decimal 903. And I see very quickly that these are all multiples of log of 2. So another way of writing log of 4 might be, just move this out of the way, might be the log of 2 squared. That's still the same thing as log of 4. Now I know the log of 2. The log of 2 is equal to decimal 301. So really what I'm doing is to find the log of 4, I could take the log of 2 and I could multiply it by the 2 from up top here. And that will give me the decimal 602, which the calculator found. In a similar fashion, I see that 8 can be written as 2 to the power 3, and decimal 903 is 3 times the log of 2. 3 times the log of 2. And that's equal to decimal 903. And I see that similar if I look at the log of 16, it looks like 4 times decimal 301, and 32 is 5 times. So this really, if we simplified this and took the numbers out, this really becomes the foundation for the power of log law. And what it says is the following. If we have a log equation with some base to the power n, then we can rewrite it as that same power times the log b. Much like we did in these situations. We took the 2, we put it in front, and then multiplied it by the log of 2. We took the 3, put it in front, and multiplied it by the log of 2. The same thing holds true. So this really is the power law of logs. There is an algebraic proof as well, and it's important that we take a quick look at it. They start by saying let w equals the log of x with the base b. Now w is just a variable, we could have picked any letter to the left here. what they did is they rewrote it as its exponential form. Remember, find the base, put it to the power w, and set it equal to x. The second step was to, because it is a power, multiply both sides by the power n. So on the left hand side we have x to the power n, on the right hand side we have b to the w, all to the power n. And through one of our exponent laws, called the power law, we can multiply these two together. So these two lines are almost the same, but we're applying the power law of exponents. From here, we would take a look back and say, well, x to the n is equal to b to the wn. If we take this and rewrite it in logarithmic form, we end up having the log of the base b multiplied by x to the n is equal to wn. Now if you look back up top here, w is equal to the log of x base b. So they're going to take that w from here and replace it with the right hand side in the next line. And we will start to reveal something much like what we did up top. So the log of x to any base b to the power n is equivalent to this n moving out in front, like we see here, times the log of x base b. So take another look, pause, go through this, make sure you can follow along with the steps involved, because there's a similar property proof that we're going to use when we look at the product law. Okay, to start the product law, we're going to be asked to fill in this table. So on the left hand side over here we have some functions: log 10x, log 100x, log 1000x, and log 10,000x. What they'd like us to do is write it out really in two different ways. So one way to do it is to do a graphical approach. And if I am to take the calculator and I am going to plug in the three remaining equations. Actually, I'll do all four remaining equations, and then we're going to take a look at the vertical translations. So this is a good time to pause, and the next screen you'll see will have all three graphs. Okay, so as you can see, the four graphs are in here, plus I've added just a standard common log of x. So all of these have a base of 10. So let's go ahead and see what they look like. The last graph that's going to be drawn is going to be a little thicker line, and that is our standard y equals log graph. So here it comes. There is the last graph. So here's our log graph, and it looks like what's happened is the log 10x has been shifted up by about a unit, and then log of 100x have been shifted up by 2 units, and then 3, and then 4. So we're going to try and write that out as they've began to write it out in this column. So it looks like our standard log x, but it's been raised to I at x. Looks like our standard log x, but has been raised 3. And finally, j at x is our standard log x raised 4. Now another way of writing 1 is the common log of just 10, because remember that there's a base 10 here, and whatever the exponent is by power law, that out in front, is equal to 1 times the log, common log of 10, which itself is really just equal to 1. So that's what this is saying here. Let's take the 1 and rewrite it as log of 10. So in h of x, it should be log of x, not plus 2, but the equivalent of 2, which is log of 100. And I of x is going to be the log of x plus the log of 1,000. And finally, j at x is equal to the log of x plus the log of 10,000. And as you can see, we can represent them both as logs, but we can break them apart. And this is really the product law. So when we look at the product law, an example might be something along the lines of this. If we have log base 2 of 12, base 2 is the same thing as 4 multiplied by 3, which can then be separated to log base 2 4 plus log base 2 3. So it allows us to separate or combine the number out in front. So this is the product law. The last law is called the quotient law, and once again there is a proof that you can run through, but in essence of time, the quotient law looks like this. If you have the log of base b m over n, so quotient is the answer we divide, that can be written as log of base b m, not add, but subtract. Log base b n. That is what our quotient law looks like. And now we can use these product and quotient law and power law all together when we're solving equations. So here's the equation for product law. And for quotient. So the log of base b m times n is equal to, and make sure those bases are the same. They could be both 2's or both 3's, but they need to be the same in order for you to apply product and quotient law. If this was something like the log of 3 plus the log of 4, we can't combine these together because they have to have the same base. If we had a situation where this base was changed and we now had a base of 3, now you can push them together because they have the same base, and 2 times 3 is equal to 6. A couple of quick examples. You can simplify by applying laws of logs. First thing we notice is that all the bases are the same in A, so usually what they say is write this as a single log. So because there's addition and subtraction, I can do this in any order. I'm going to do the addition first, which is my product law for the first two. So that's going to become 6 multiplied by 8. And then I'm going to take an extra step here, but eventually you will need to. And so I end up with log of base 5, 48, subtract log of base 5, 16. The minus sign means because the bases are the same, I can push these together using the quotient law, and it becomes 48 divided by 16, which I can evaluate to become 3. And so once we, in the next video, we'll learn how to use the change of base rule, which will allow us to solve this question. Here's an example. We'll just do A, where we can evaluate. So once again, I can do this in a number of different ways. One way I can do it is to recognize that the bases are the same. So I can push the 4 and 16 together by multiplication, product law. 4 times 16 is 64, and this works out quite nicely because I can write 64 as 8 squared, apply the power law, which says I can take that 2 and move it in front, and I end up with 2 times the log of 8 to the base 8, which is equal to 1, so it's really 2 times 1, which is 2. And you can try the question B and question C down below. These are good questions. Solutions to these are in the textbook as well. Here are some of the key concepts. Please have a look at some of the example questions in the textbook. And here is your question bank, or you can check my website to see a more updated list of